Okay, and we're ready to go. We were right in the middle of the problem last time, so let's actually just finish that up. Let's see. So the goal was to maximize. I mean, I'm just recopying what I said before. This function of x and y, x plus 2y, and we had the constraints of the following. 2x plus y must be less than 2, or equal to x plus y must be less than 13, 2x plus 5y must be less than 50. X greater than 0, and y greater than 0. So these are the constraints. That's the function I care about. That's called my objective function. I want to maximize it given that these criteria are true. And step 1, as we said, was to find a feasible region. Which involved sketching, and it involved a very bad sketch, because that line did not look straight at all that last one. But let's try to get this. So I want to say it was something like this. It's No.
No.
This one ran over.
Erase the one that you just did.
Okay.
And then there's one on
It's
the bottom.
Yeah.
More like
It's below. It's below the
It's
second
below, but
yeah.
then goes above that.
it was like really close to the intersection.
Oh, I want this guy to be that, the last bad one.
Oh, okay. So,
So-
they're in between those two.
So there's another one in
Yeah,
between
yeah.
here going where?
Going straight down like that.
Down here or down
It
there?
has to
Like down there.
Down and in between the other two.
It creates a triangle below. So
Oh, it creates a triangle down here.
Yeah.
Okay, so.
no.
You have to start over by plotting all the points I want to avoid.
Okay, the points are 22, 13, and 10. On the
Okay, so
y-axis.
let's just start plotting points again. The first one is y equals 22. 22.
11.
Oh, it's 11.
You go all the x-axis.
And then on the x it was 11. It's like that. Then the second one it's 13 and 13.
Yeah.
And then the next one
10 and 25.
was 10 and 25.
No. 10 is on the y-axis.
Y equals 10, yes, okay. And it went like this.
Yeah.
It's like supposed to connect, but like not drawn to scale.
I think it was supposed to hit this one first, right? I think.
Yeah.
The 13,
Yeah,
13?
yeah.
Yeah, okay. Again, not straight, but whatever. And this was the 25. And that's our feasible region, right? This little triangle right here.
Why wouldn't your feasible region be the area below? If all of the three lines are less than.
I know, I feel like that's what I shaded last time. Or did I shade?
Yeah, but I was wondering why.
Okay, so let's actually think about this from scratch. We want to be below this line and below that line. We also have the x and y axis in play. Yeah, we literally want to be below all the lines, so that actually wasn't one. Because this area would be above this line. Here. Right? It's below this, it's below that, it's below this, it's above the y, it's to the right of the x equals 0. So the points around us are these guys here. And I believe this one we already computed. What did we find that to be?
5, 8.
Huh?
No, it's 5, 10.
5, comma 8.
Yeah.
And this one we automatically know because that's an x intercept. So this is 11, comma 0. This one is of course the origin, 0, comma 0. This one is 0, comma 2.
Yeah.
So
Nine.
now we need to know this one.
9, 4.
Oh, did we already find that too?
Yeah.
Oh, wow. Not farther than I thought. Okay, cool. So, yeah. So that was step 1, to actually figure out what region actually satisfied our constraints. And step 2, what did I write for step 2?
Find the corner.
Which we did. And you just do this by, we did this by solving the systems of equations. Okay, so if I wanted to find this corner point, I just take the equation of this line, intersected it with the equation of that line, so we found the solution to that system. And then to find this corner point, I want to take the equation of this line and intersect it with the equation of that line. And to just set up a system of equations, you'll have to solve for 2 of them, 2 systems, and hopefully by this point you can do that relatively quickly. And then the others would be obvious because they're actually intercepts. But here, notice here we have 5 corner points. Now, what do we do once we find the corner points? It turns out, and this is something that I'll justify later, as it turns out. The corner points will be where our solution is going to occur. This is actually a theorem. Optimal solution for a linear programming problem. For a bounded region. Remember we mentioned that there's a difference between those. Bounded region occurs at a corner point or edge of the piece of the region. I'm going to justify that to you later, but right now I'm just telling you that's the answer. If you want to maximize or minimize a linear function over some sort of region defined by linear inequalities, your answer is either going to be located at one of these corner points, one or several of them, or every point along one of the edges, maybe like every point on the line between these two will actually be the solution. Right? Now I'll tell you why in just a sec, but let's actually just finish this problem. So that's step 3. Step 3 will be to evaluate your objective at all corner points. basically what you can do is you can set up like a table to do that, just to keep things organized. Your x, your y, and what your f of x, y is. And you are going to have here 5 situations. 1, 2, 3, 4, 5. So we can have x equals 0 and y equals 0. Or we can have x equals 0, y equals 10. Or we can have x equals 11, y equals 0. Or we can have x equals 5, y equals 8. Or we can have x equals 9, y equals 4. These are all the possibilities. And what I'm going to do is I'm going to plug that into the original function, which I believe was 2x plus 1. X plus 2y. I'm going to actually compute the value for each point. So I can x plus 2y, if both are 0, well, that's 0. What is x plus 2y in this case? No, I plug in x equals 0. I plug in y equals 10.
20.
I get 20. If x equals 11 and y equals 0.
11.
If x equals 5 and y equals 8.
21.
Right, because that's 5 plus 16, which is 21. If x equals 9 and y equals 4.
17.
Now these are all different numbers, but as you will notice, only one of them is the biggest number. The biggest number is unique. Basically what that means. This point is going to be our maximum point. So that brings us to step 4. You're going to make a conclusion based on the values of the table. Chances are if you had the two of the same numbers at 2 different points, it would actually be the same value going along that entire edge connecting those 2 points. But that leads us to step 4. Include what the optimal solution is. Based on the values in the table. 3. Here we want a maximum. This means the solution to our problem is the following. The maximum value of x, of our f, is going to be 21. It occurs at the point 5, 8. On this feasible region, the biggest that function will get is a value of 21. It will not output any value higher than 21 as long as you're over that shaded region. Did you have a question?
Yeah, how do you know to use x plus 2y?
Oh, that was given. So that was in the question. If you read the statement of the question, it says maximize this function with respect to this constraint.
Oh, so maximize x plus
Yeah.
2y.
So this was given, and I say find the maximum value of this thing if we were forced to assume that all these inequalities have to be true. Right? Now, it's not always going to be given, but you will be given enough information to figure it out, which is where we're going to go. Right? This is just how you'd actually go through a problem, but setting up the problem, you're going to be required to do that yourself as well. So pretty much what we're aiming for here is I'm going to give you a word problem. It's going to describe a situation. You're going to read that word problem, figure out what's the thing you need to make biggest or smallest, and what are the restrictions. Once you write that down, then you're going to do this, and you're going to be able to say a certain answer. If you want the biggest value, here's where it's going to happen. This is what you need to do to be able to answer the problem. Any other questions based on the process here? So you're given a function which is some objective function, or you find the objective function. You have a bunch of restrictions which are given by inequalities. Certain things have to be less than this, certain things have to be greater than that, whatever. But step one is to find the feasible region. It's going to have you sketching a bunch of lines and figuring out what region of space satisfies all the restrictions. Step two is actually locate the corner points, because step three is to evaluate the function at all the corner points. It turns out that the corner points or an edge will always give you the answer. And step four, you make your conclusion based on that. So if the question was instead, what is the minimum value? The answer would be 0, which occurs at the origin. So now let's actually answer the question why. Why is it that the corner point gives us the answer? Now, this is not really the kind of class where we do like really rigorous, intense proofs. So instead what I will do is I will try to convince you of this using an illustration. I'm not going to actually prove it for you, but my hope is by showing you this example, you're going to see why it must be so. So it's not a proof, but we'll suggest why this is true. With an illuminating, hopefully, example. So say our objective was this. Say x plus y as an example. So that's y. Right? So now each time f takes on a value, right? You plug in some x and y and you compute f, right? It results in, well, the thing it results in, you actually know what that is. So let's say f takes on the value 1 at some point, so I would get x plus y equals 1. Or let's say f takes on the value minus 5, so you get x plus y equals minus 5. Or f takes on the value 3, you get x plus y equals 3, etc. Right? F can take on any value depending on what you're plugging in for x and y. But what do all of these guys have in common? What are they? They're just lines. They're straight lines. If you have a linear objective function, once your function takes on a value, you're looking at the equation of a line. So what you actually have here is you can imagine that these lines for different values of f, you're just creating lines. Like an example would be x plus y equals 1, or x plus y equals 3, or x plus y equals minus 7. You can, in fact, x plus y equals 0. You can create an infinite number of lines here, right? So we have each f value creates a line because they are linear. And of course, as you can see here, the higher up I move it, that means the bigger the value, right? Bigger values go towards the top, smaller values will go towards the bottom, etc. Right? So I can just take the line x plus y equals k, some constant, right? X plus y equals k, because the answer is in fact, if I plug in a value for this function, I get a line. For different k values, I'll just get the same line with the same slope, but they'll have different y-intercepts. Now, of course, as you can see for this particular example here, the highest output corresponds to the highest y-intercept. right? So if I want to move up, if I want to get my function to be bigger, move up. If I want to get my function to be smaller, move down. Now imagine that there's a feasible region in this graph. If I want the line to have the largest value on that region, what am I going to do? Is it going to happen in the middle? Well, the answer is no, because I can just shift the line up and get a bigger value. And I can keep shifting the line up. Now, eventually what's going to happen is the line is going to shift up so high that it's going to pretty much be on the teetering edge of leaving the region. If I were to go up any higher, I'm now outside the region. If I were to go down any lower, I'm now not as big as I could be. The perfect situation is to be on the edge, right? Conversely, so this will be where the maximum will occur, just by me moving the line up. If I wanted to find the minimum, well, I'll just move it down. And it's going to hit a point over here on the edge, right? Now that edge point might be a corner, because everywhere else is going to be farther away from this line, or it could be itself just a straight line running along that guide. So if you're in this situation, every point along this edge will give you a maximum, whereas if you're a sharp corner, only one point is going to give you the max or the min. And basically you can figure that out simply by shifting your line up or down. Yeah.
Are the lines tangent to the point? Is it a tangent line?
No, tangent line wouldn't be the right name to say, but it is in fact passing through. The highest line that still remains within the region is going to give you the maximum, while the lowest line that still remains within the region is going to give you the minimum. And no line in the middle is going to do that, because you'll always be able to move up or down and get something bigger or smaller. So there will never be a coordinate that's in the smack dab in the middle of your region that's going to be the answer. The answer has to be on an edge, right? Because anywhere in the middle, you'll be able to shift up or down to get a bigger value or a smaller value. And so, yeah, the answer to the maximum or minimum question always happens on an edge in a linear programming problem. And the edge might itself be a corner point. Now, that's for a bounded region. For an unbounded region, that's not necessarily true. So, I think this could be said in the same theorem. So, the optimal solution to a linear programming problem will occur at a corner point or edge or bounded regions. For unbounded regions, the max and or the min might not exist. So one big difference between bounded and unbounded regions is that your bounded regions will always have a solution. Just keep shifting up until you hit an edge. But what if there is no edge to actually hit, which happens to be the case in an unbounded region? So if I look at this same principle, the same idea, where I just have a bunch of lines that I can shift up and down to get bigger and smaller values at will, but instead, my region is, let's say, the entire first quadrant. Right? Now, what is going to be the map? Now, in this situation, f of x y equals x plus y does have a minimum. It has a minimum here. Namely, it's f equals 0 at the origin. Right? That's going to give you the minimum point. However, what is the maximum? Well, to get the maximum, I'm just going to keep shifting this thing up until I get the biggest value possible. But guess what? You'll be shifting it up forever because this green shaded region never ends, right? No matter where you are at the line, you can shift up higher and you'll still be inside the shaded region. And you can just do that forever, but it has no max. So there are times when you'll have a linear programming problem that has no answer. And if that's the situation, it's because you have an unbounded region. So the unbounded regions, you have to kind of be careful because you may or may not have an answer, and that's going to be important. So you can test all your corner points and they'll give you values, but it's possible to find a value that is not among the corner points, that is bigger or lower than any one. So that's pretty much, that's the gist of it. So once we draw a feasible region and have a linear objective function, shifting the line up or down gives us the max or min. This guarantees that the max or min will occur at an edge or a vertex. And that's how we solve the linear programming problem from a graphical standpoint. Of course, we use systems of equations to help us out. So, any questions about the process itself? Like the processing method? You don't need to know why I just showed you because you can. Any questions about the process, what you would do? No? Okay, good. We're all on the same page. So yeah, you want to solve a linear programming problem? Well, first of all, you're going to figure out your objective function, figure out your restrictions, you're going to sketch these to find the feasible region. Then you're going to use systems of equations to find the corner points. Then you are going to evaluate the objective function at these corner points to see where your maximum or minimum occurs. You take whichever one is necessary to solve the problem. And if you happen to have an unbounded region, it is possible that the solution does not exist, so you have to be very careful. That summarizes it. Let's actually do some problems. So if a linear, pass these around, sorry about talking. So if a linear programming problem shows up on a test, it will be presented to you in one of these kinds of things here. Does everyone have one?
Maybe one more.
You need one more? Okay, so these problems will come to you as word problems. So there are 4 here. We're definitely not going to get through all of them today. So if anyone spills out on over to Friday, we'll finish up then. But yeah, they'll come as word problems. They'll describe some sort of situation or dilemma that someone has, and you need to solve it based on a linear programming problem. Because it turns out, once you start to apply math to all these situations, you just get a bunch of lines and linear inequalities. And that happens more often in real life than you'd imagine. And so a linear programming approach to these things is very common and very useful. So let's actually do one of these. Okay, so animals at a rescue center must have at least 30 grams of protein and 20 grams of fat per feeding period. So every time you give these animals a meal, that's how it has to, that's the macro split right there. The shelter has 2 kinds of feed, food A and food B, and these are what they have contained. So food A contains 2 grams of protein, 4 grams of fat, and it costs 18 cents per unit. Food B has 6 grams of protein and 2 grams of fat. That costs 12 cents per unit. Now, food B is bought under contract, so at least 2 units of B must be served per serving. So the owner of the rescue center works out a deal with the supplier of food B and says, hey, I'll buy this amount of food from you for sure if you give me a deal on the price, okay? So sell it to me for 12 cents per unit and I'll make sure I'll buy at least 2 units every time I need to feed these animals. Okay, Another contract requires that the amount of food B used per serving not exceed 3 times the amount of food A. So, you might have also noticed that food A is more expensive than food B. Probably food A is of better quality. And PETA comes in and be like, you can't be serving these animals this crap. You know, if you want to do it, I understand costs and all that stuff, but no, give them some of the good stuff and don't let the bad stuff pass 3 times this, because it's just not fair to the animals. Okay, so you're buying food B under contract and you're not allowed to serve more than 3 times food B than you give in food A. So that's the situation. Now, here's the problem. How much of each food must you buy to have the minimum cost? Right? You don't want to go into debt trying to help these animals. You want to help them and continue to be able to help them, and you need to be smart with your money. How can you provide for all these restrictions and still not spend more money than you have to? That's the situation. And it turns out this is a linear programming problem. So let's set it up. So problem 1 from handout. By the way, I posted an electronic version of this on the class website. So in case you lose the physical handout, you can go there and print it out. Okay, the Animal Rescue Center problem. Okay, so let's start with what is our objective function based on the things here? What is the thing we need to maximize or minimize? What is the goal? Like in words, what do you want to do? Yeah. Right, you want to minimize cost. How can I find the cost? What is the cost per serving? Yeah.
It's X times 18 cents Y plus 12 cents.
So 0.18 times X plus 0.12 times Y is going to be my cost function. So I want to minimize that, where X equals the amount of food A per serving. And Y equals the amount of units of B per serving. Okay? Now if I serve X units of A and Y units of B, this is what it's going to cost me to provide that meal. Notice it is a linear function. What are the constraints though? Now, 2 should be kind of obvious, and that will be the case in most problems, but X and Y greater than or equal to 0 should be obvious, right? I'm either going to serve none of these units of one of them, or something larger. I can't serve negative units of a food. So those are going to sort of be automatic almost in all problems, and it works for this one here. But what are the other restrictions?
You have to have at least 30 grams of protein, 20 grams of fat.
Okay, how can I describe that in terms of X and Y? Yeah. X is greater than 30 and Y is greater than 20? No, because that means you can have 50 units. Okay, so let's read this very carefully. This is where the hard part comes in, trying to figure out what the hell you have to set up to actually solve the problem. So let's look at this at the restrictions one at a time. Let's start in sentence 1. You must have at least 30 grams of protein. So let's start there with the protein. Okay, so total per serving must be at least 30. Okay, means 30 or more. So what is the total amount of protein per serving? If I'm serving X units of A and Y units of B, what is the total amount of protein? Yeah.
2x plus 6y.
2x plus 6y. We have that food A has 2 grams per serving. So for every x units, there are going to be 2 grams of protein. And if I look at the food B, it has 6 grams per unit. So that's 6 times however many units. So that is one restriction. 2x plus 6y must be greater than or equal to 30. Then I do the same thing for the fats. So now I see that the total fat must be at least 20. What's the total fat?
6x plus 2y.
Right, 4x plus 2y by a similar rate. I get 4 grams of fat per unit of A and 2 grams of fat per unit of B. When I mix these together, I better have at least 20 units of fat. Okay. Other restrictions. So food B is bought under contract requiring at least 2 units of B per serving. What does that tell me? The y must be greater than or equal to 2, and that's by contract on B. Any other restrictions? Yeah.
Y is less than or equal to 3x.
So y must be less than or equal to 3x. You cannot give more than 3 times y to be x. And so that is the contract on A. And that's it. So it turns out, reading this problem, you can feel, how am I supposed to figure that out? Turns out when you start to actually write down the mathematical translation of the situation, you end up with a linear function that you need to minimize in the presence of linear inequalities. So this is a linear programming problem. So you're supposed to read that word problem. You're supposed to figure out this is what you want to minimize in the presence of these. And then you're going to actually do that. So let's begin. So step 1, we're going to actually try to sketch things here. We're not great at it, but we have to practice. Okay, so some of them are easy. X equals 0 and y equals 0. Those we'll definitely have. Okay. Y must be greater than or equal to 2. So let's put here. Let's make that a 2. Of course, it's not drawn to scale or to actual specifications. It's just to give us an idea. What else do we have here?
Well, you got 3x.
Come again?
Can't you draw in y less than 3?
Y equals 3x.
Yeah.
That is just a line going through the origin. Okay, so this is y equals 2. This is y equals 3x. Let me break them apart. Alright, so everyone here has been drawn. Now we get to the tough guys here. So I want minimum of 0.18x plus 0.12y. Let me clear up some space here. X is the amount of food A and y is the amount of food B. Okay. So let's start with this one. So what's the x-intercept here? 15. And the y-intercept?
5.
Is 5. So like that. Now, this is probably not going to be a solution, but I just want to know for now what this point is. Where does it actually intersect that point? So we have, for this point, I want, one has y equals 3x, the other has 2x plus 6y equals 30, or in other words, 3x minus y equals 0. And I can divide this through by I can divide this through by 2. So you can actually multiply this by 3. That's 9, 45, and subtract 1 from the other. So this minus that, you get 0. This minus that, you get 10y equals 45. Is that right? And so your x is going to be 15 over 10. Does that make sense? So 3 times this, you do get that. If I take 2 times 15 over 10, and I add that to 6 times 45 over 10, what do I get here? Well, this is 30 over 10. 6 times 45 is what? You get 270. And so what you have, you get 300 over 10, which is 30. Right? So that actually works. So this is like 4.5, and that is 1.5. And I can, so I know that this actually occurs at x equals 1.5. And it occurs at y equals 4.5. Now that might not be a corner point for my region, I just want to know location-wise where things are ending up. Okay, what else do we have? Let's go with the other one. This guy, x-intercept.
5.
5. So it's going to be bigger than this. Y-intercept. 10. It's going to be bigger than this. Now, I have the hunch that it's going to intersect above here, but let's actually make sure where that intersects. So let's intersect these two. See what the actual y value is going to be. So x plus 6y equals 30, 4x plus 2y equals 20. I can reduce that by 2. And reduce this by 2. You could also do a matrix version if you want. So that's 1, 3, 15, row 2 minus 2, row 1. That's going to be 0. This minus 2 times that is minus 5. 10 minus 30 is going to be minus 20. So our y will be 4. And our x plus 12 is going to be 15, so our x is going to be 3. So it actually cuts this one at a lower value. It'll actually go over. So this is this is 3x. Which 2 did I intersect? I intersect this one, which is, I'm gonna write this down. This is why I have to label them so you don't get mixed up. What is this one here?
2x plus 6y
Equals 30. Okay, so I want to intersect this line when the output is 4, which means I should be intersecting it over here. So yeah, intuition kind of worked out there. So this y value here, that's going to be lower, that's at 4. And the x value here is going to be 3. So we have that kind of situation. That's a crazy one. Like on a test, I'll probably give you less lines, but okay, that's for this one. Okay, so where is our feasible region? For these two, This here is 4x plus 2y. I want to be above this. I want to be above that. I also need to be above this, so all of those guys are pointing up. What about the 3x? I want to actually be below that. Okay, so what is above all of those guys but below that? So this region here. Right? So it turns out that all of these are my corner points. This, that. Now it turns out our objective function is going to be aligned with negative slope. So it's not actually going to have a maximum. You can spend all the money on these animals you want, but there will be a minimum. It's going to occur at one of these 3 locations. So, what do we know this location? We do know this location because that's just y equals 2, right? So that means if I take the 2x plus 6y, plug in y equals 2, that will give me 12. Move the 12 over. 30 minus 12 will give me what? 18. Divide by 2 will give me 9. So this here is 9 comma 2. So now I'm going to do that table. X, y, and I want f equals 0.18x plus 0.12y, and I have 3 locations to check.
Yeah, but you didn't get the fourth one.
What fourth one?
The topmost blue one we have.
Oh, what is that? This one here? 2 comma 6. Yeah, you'd have to find out. Okay, so let's just rush because we only have a few minutes left. Yeah, so we have to check 2 comma 6. We have to check 3 comma 4, and we have to check 9 comma 2. Okay, so now plug this into your calculator. 0.8 times 2 plus 0.12 times 6. So what is the first one? 1.08. 1.02. $1.86. Now this is the cost per serving. So what's the cheapest?
3 and 4.
This situation. So the minimum cost per serving is going to be $1.02 per serving. This will occur if I feed the animals 3 units of A and 4 units of B. I will obey all contracts. I am serving at least 2 units of B, and the number of units of B is not more than 3 times the units of A. And that satisfies the entire situation. Think about part B. We'll talk about that. That's more of a business question. See you guys on Friday. We'll do the rest of the examples. You can try them ahead of time. It's probably better.